Alright, so page 2 of the review here, first question, says if you take a bite of hot pizza, the sauce may burn your mouth, while the crust, which is at the same temperature, will not. So the crust and the sauce have been in the oven both for 20 minutes, so they're both 400 degrees, or however hot the oven is. Explain why the sauce burns your mouth. Alright. And so this kind of has to do with the idea of heat capacities, or specific heat. Water has a much higher specific heat than bread does. Water has one of the highest specific heats out of pretty much every general everyday substance. And so when you put the pizza in the oven, that water is going to take a lot more energy to heat it up. So even though they're both going to 400 degrees, the water is taking in a lot more energy than the bread is. So the water is absorbing a lot of energy, even though the temperature change is the same. Therefore, when you take it out and you bite it down, now you put it in your mouth, now it's got to cool off, and the water has a whole bunch of energy that the bread doesn't really have, or the crust. The crust has some energy, but it's not as much as the water, because the water has a higher capacity to hold that energy. And so whenever you bite it, the sauce releases a lot more energy into your mouth than the crust does, and so the sauce is going to burn. The crust is going to be nice and toasty. It's going to steam nicely when you break it. I love pizza. So that's kind of, I didn't really write that down. In a nutshell, though, this has to do with the heat capacity of the sauce is much greater than the heat capacity of the crust. Alright. Similarly, number 2, same principle there. It's a cold night. You wish to keep your feet warm. It's a common trick that campers use. And on a cold night in a sleeping bag, how do you keep those toes warm? Fill up a water bottle full of hot water, and it's going to keep its temperature a lot longer than the brick will. So again, it kind of has to do with heat capacity. Since the water has a higher heat capacity, it's going to, I guess you could say, it's going to be a lot harder to change temperature. And so the iron brick is going to lose its temperature, it's basically the temperature is going to change much quicker because the brick's specific heat is a lot less. All right, and remember we kind of talked about in class that specific heat or either heat capacity is similar to thermal inertia. And so since the water has more capacity for heat, its thermal inertia is a lot more, so it's harder to change the temperature of the water. So it's going to retain its heat for longer than the brick. So, number 3, why does adding the same amount of heat to two different objects not necessarily produce the same increase in temperature? There's a few, I guess, ways that this could be true. First off, so heat, remember heat depends, this is my Q for heat, the mass of whatever heating up times the heat capacity of the object times the change in temperature, commonly referred to as MCAT. So heat is energy, depends on the mass, specific heat, and the change in temperature. So if you add the same amount of heat, it might not necessarily produce the same temperature. Well, let's say the masses are different. One reason is because the masses are different. Masses are different. For instance, if you have a gallon of water and you have, say, a cup of water or a teaspoon of water, if you add energy, the same amount of energy to both, the teaspoon is going to get hotter much quicker. By hotter, I mean the temperature is going to increase much more than the gallon because there's more mass of water to heat up, so the energy can't heat the whole gallon up all at once, so the temperature doesn't really increase all at once. So we talk about heat transfer, the fast-moving molecules bumping into the slow-moving molecules. If there's a lot less molecules to speed up, then they can all speed up faster. So if the masses are different, that might explain why the increase in temperature is the same. And second reason, it could be that, again, the heat capacities are different. So heat capacities are different. And again, similar thing with the well, I guess these questions are a little bit different relating to heat capacity. But if you, let's say you give about 4,000 joules of energy to a brick of water, or I guess whatever sort of brick of water you may have, some water and a piece of metal, the water is going to, or the metal is going to increase its temperature by a lot more. Because if it has a smaller heat capacity, then it will take less energy to heat up. All right, and you can do some calculations, but just in a conceptual point of view, if it's harder, if it takes more energy to heat up certain components than if you have the same amount of energy to things, then they might not increase by the same amount of temperature. All right, so what do we have? Number 4. Suppose you use 1,500 watt iron for your clothes, and the iron has a 1.5 kilogram stainless steel plate. Specific heat capacity of stainless steel, or specific heat capacity, that's bad terminology there, excuse me. And it's 510 joules per kilogram degree Celsius. Suppose you turn the iron on for 180 seconds. How much energy is produced? This is actually a two-part problem, part A up here and part B. So, how do we determine energy? So we know that, okay, heat energy, MC delta T, but we don't really know, we know the mass, we know the specific heat, but we can't really determine how much heat is produced if we don't know the change in temperature. So what we can do though is say, well, we can determine electrical energy, and from the first page in our notes, we remember that electrical energy is power times the time. So if we give, well, conveniently, we have the power, 1,500 watts, and the time that it's on, 180 seconds. So using that, we can determine, hey, how much should we use? 270. So 270,000 joules of energy. And now part B says, and this is going to come in handy, because now we want to find temperature change. We know that it's initially at 20. What is the final temperature after it's on for 3 minutes? How long, or how much does the temperature increase? And now we can use our heat formula. And we say, assuming that, it's 100% efficient and all of the energy, the electrical energy goes to heating it up, we could say, well, if the iron produced 270,000 joules of energy, that energy could go to heat up the iron, which is nice, because we could say we have 270,000 joules of energy put into it, and that 270,000 joules went into 1.5 kilograms of a metal with 510 joules per kilogram degree Celsius of specific heat, multiplied by the change in temperature. And you can find that the change in temperature is 270,000 divided by 1.5 divided by 510. Oops, not plus. Equals 352.9. Around that to 353. Degree Celsius. Now, one slight little trick at the end. This is the change in temperature, delta T. And so if we started at 20 and we changed our temperature by 353, that means that our total difference or the new temperature is 20 plus 353, which is 373 degrees Celsius. So a little trick at the end. Sorry, that'd be tricky. Another way you could have solved this is instead of writing delta T, you could have said, okay, well, this is temperature final, whatever the final temperature is, minus 20. Remember, delta means final minus initial, so final temperature minus the initial temperature of 20, and you could have solved it that way. You would have received 373 degrees centigrade. All right, what do we got? This, I believe this one is a straight heat calculation problem. So gold melts at 10,050 degrees. It's actually about 1,063 or 64, I believe. I looked it up a little earlier. And it has a heat capacity of 126 joules per kilogram degrees Celsius. How much heat does it take to melt this much? Piece of gold was originally at 20 degrees C. So gold right now is, well, last time I checked, it was like $1,500 an ounce. So if you want to melt that $1,500, how much energy you got to use? So we have M, C, delta T, mass of it, 0.0311 kilograms. Specific heat of gold, 126 joules per kilogram degrees Celsius. Change in temperature. We're starting at 20, and we have to go to 1,050. So 1,050 minus 20 is our change. We can crank that out to get, well, that's just 1030. 4,036 and some change joules. Last question. Explain what thermal expansion is and give some examples. We did talk about this a lot in class. Remember, thermal expansion happens basically when you heat things up, things expand. So, heating objects causes expansion, causes things to expand. Examples. Talked about bridges. Those little, when you drive over a bridge, you know, those little gaps in that bridge. That way, when it gets really hot outside, the bridge can expand without the bridge crumbling. And actually, you know, if it doesn't have anywhere to expand, then the concrete's going to break, the asphalt. So what do we got? So we got bridge, gaps, for bridges in general. What else do we have? We did a little experiment where we had a brass ball that fit inside of a brass ring, and we heated up the ball, and it didn't fit anymore. After we heated up, the ball expanded. The ball and the ring experiment. Sometimes it's hard to put on rings in the summertime because your skin expands. Or in the wintertime, maybe the rings are a little loose because your skin contracts. So rings are loose, or rings are hard to put on in summer. Train tracks, I think I showed a picture of that. Train tracks can warp sometimes in extreme heat, unless they put little gaps every so often, etc. Alrighty, so hopefully this helped you out, and if you are watching this, hopefully this helps you succeed on your test. So good luck, and I will see you all soon. Thanks.